Hey everyone, and welcome back to another Explainer. I am so incredibly excited you're joining me today because we are going to unpack something that is literally all around us yet completely invisible. We are looking at the invisible engine that runs our modern world. Think about it. Most of us walk around every single day interacting with the end results of incredibly complex systems, right? The clean water coming from our taps, the steady electricity keeping our screens glowing, all those mass-produced goods we buy without a second thought. We use them without ever stopping to consider the massive hidden networks of control making it all happen. So today we're shedding some light on those invisible forces. We're going to explore the wild world of industrial automation, how it started, how it actually works, and why human survival literally depends on it.
55 million. Now, that is not a dollar amount, and it's definitely not the population of some small country. Back in August of 2003, 55 million is the exact number of people who suddenly, and with absolutely zero warning, lost their power in the Northeast blackout across the US and Canada.
Okay, let's really dive into this. When the lights go out and the machines stop running, this eerie stillness falls over everything. During that 2003 blackout, life as we know it essentially ground to a halt. Transportation completely stopped. Water treatment facilities couldn't operate, and tragically, 11 people actually lost their lives. That catastrophic event proved exactly how entirely reliant we are on automated control systems. I mean, when the invisible engine stops, society stops. It's a pretty sobering reminder that automation isn't just a way to make factories pump out widgets faster. It is the very backbone of our critical infrastructure.
So part 1, defining the invisible engine. Let's get a handle on what we actually mean here.
At its core, industrial automation is all about handing the reins over to the machines. It's the use of control systems like computers and programmable logic controllers, which we'll get into in a minute, to operate industrial processes and machinery with little to no human intervention. The whole goal here is to remove the human hand from tasks that are repetitive, dangerous, or just need to be highly precise. And by doing that, we dramatically improve efficiency, consistency, and above all else, safety.
Now, if automation is the big picture, process control is the nitty-gritty moment-to-moment mechanism that makes it work safely. It's the automatic control of a process variable to a specific desired set point. So picture a massive chemical plant or a power generation facility. They're dealing with incredibly volatile physical elements. Process control is like this invisible hand constantly tweaking the temperature, adjusting the pressure, the flow rate, the liquid levels, ensuring everything stays exactly at its safe set point. And it does this using sensors, controllers, and actuators. It's all about maintaining perfect balance.
Moving on to part 2, the 4 industrial revolutions. To truly appreciate where we are today, we need to take a quick trip back in time.
Because, we didn't just wake up one day with computers and smart factories. We had to move step by step. We went from early mechanization in the 18th century right through the age of electricity, into the dawn of computing, and finally to the highly networked cyber-physical systems we use right now. Let's actually look at how this builds, step by step, using a really simple equation for each era.
Here is our first equation of progress. Back in the 18th century, we took good old-fashioned manual human labor and we added steam and water power. That combination birthed the first industrial revolution. For the absolute first time in human history, we were laying down the physical groundwork for automated manufacturing.
I mean, just look at how intensely physical and mechanical these early setups were. On the left, you've got your classic water wheel, literally capturing the kinetic energy of a rushing river to grind grain or run a sawmill. And over on the right, you have the magnificent Jacquard loom from 1801. This thing is a brilliant early example of automating a complex process. It actually used stiff pasteboard cards with punched holes to instruct the loom on how to weave intricate patterns, a total game changer, but still entirely mechanical.
Then, our equation gets an upgrade. As we moved into the late 19th and early 20th centuries, we took that early industry and we added electricity. Bam! The second industrial revolution. Suddenly, factories didn't have to be built right next to rivers for power anymore. We could build assembly lines, and we finally achieved mass production. This shifted the global economy forever.
But the real leap, the one that sets the stage for the world we live in today, happened in the late 20th century. We took mass production and we added computing. This is the third industrial revolution. By bringing computers onto the factory floor, we weren't just powering machines anymore. We could actually monitor and control them intelligently. This gave birth to SCADA systems, allowing operators to oversee massive, sprawling industrial operations from just a single screen.
Which brings us to part 3, from relays to PLCs. Let's kind of pop the hood here and look at how these brains actually evolved.
So, how did these machines actually think and make decisions before computers came along? Well, look at the sheer physical complexity of this early 1900s setup. What you're seeing here is a relay-based logic system. Before digital computers, if you wanted a machine to do a specific sequence of tasks over and over, you literally had to hardwire a massive board of mechanical switches and relays, just like this one.
The problem? The limitations were absolutely massive. Because they were entirely hardwired, if you wanted to change the manufacturing process even a tiny bit, you had to shut the entire factory down. Then electricians had to come in and manually rewire the whole board. It was a nightmare to modify and almost impossible to scale. But then, in the 1970s, everything flipped upside down with the introduction of the PLC, or Programmable Logic Controller. PLCs use microprocessors, so instead of physical rewiring, you just write new software code. It gave us programmable, flexible, and instant control.
Just look at the crazy physical contrast here. On the left, that messy, room-sized, dust-collecting mechanical relay board of the past. And on the right, a clean, super compact, highly efficient modern electronic board. Fun fact, the very first PLC, called the Modicon 084, was invented in 1968, and it completely revolutionized industrial control. We basically replaced all that mechanical clunkiness with sleek digital elegance.
All right, part 4, SCADA and the IoT. Let's look at modern automation and how we actually link all this stuff together.
So we have these brilliant, flexible PLCs controlling individual machines. But in a massive, modern facility, say a citywide water network or a sprawling regional power grid, you need a way to link those isolated controllers together. That is where SCADA comes in. It stands for Supervisory Control and Data Acquisition. The way it works is by constantly scooping up data from sensors all over the plant and sending it back to an energy management system or a central server. It's run from highly centralized control centers, which means just a few operators can keep an eye on a massive footprint. We use it to gather real-time data, voltage, current, system status, the whole shebang, and to perform remote actions instantly without someone having to physically walk over to the machine.
Follow this continuous loop with me for a second. You have sensors out in the field gathering data about a physical process. They feed that data back to the controller, our PLC. The controller checks that data against the desired set point, and if things are even slightly off, it sends a command to the actuator, which physically tweaks the process. Then the sensor reads the new state, and the loop just keeps going, endlessly and automatically, multiple times every single second.
Which brings us to our fourth and final equation, the fourth industrial revolution, also known as Industry 4.0. We take the incredible monitoring power of SCADA and we merge it with the internet and cloud technology. This mashup gives birth to the Industrial Internet of Things, or IoT. Now, these systems aren't just automated, they are remarkably smart. They're interconnected globally, and they can analyze massive amounts of data in the cloud to predict failures before they even happen. It's wild.
So, the big question, why does all of this actually matter to you and me? Well, first, it vastly reduces operational costs and cuts way down on human error, which means the products and utilities we use every day are more reliable and affordable. Second, and honestly most importantly, it keeps human beings out of dangerous situations. We don't have to send people into toxic or high-voltage environments anymore. And finally, all this real-time monitoring allows for much smarter, faster decision-making, which keeps our critical infrastructure perfectly stable.
We have journeyed a long way from wooden water wheels to cloud-connected control centers, haven't we? These invisible systems are absolute marvels of human engineering, and they literally make our modern lives possible. But they also create a really profound dependency. Thinking back to those 55 million people left sitting in the dark in 2003, I want to leave you with one final thought to chew on. As our world becomes entirely reliant on these interconnected cyber-physical systems, are we truly prepared for the next time the invisible engine stops? Thank you so much for joining me on this explainer. Keep learning, keep asking questions, and I'll see you next time.